Hello, everyone. Welcome to this week's Green Bank Observatory Community Zoom. Just a couple of announcements before getting to the talk. So we are in the middle of summer maintenance season here at Green Bank, and even as we speak, we have a company who's come in and is working on replacing sections of our foundation on the Green Bank Telescope. This is part of a plan to replace the entire foundation. We've already replaced a couple sections of the foundation, and we're extending that work this summer. Next week we begin our triennial structural inspection of the telescope, and that should take several weeks. And we do this every 3 years to make sure that the telescope structure is sound and to act on any issues that the team finds. So it's a major undertaking, but it's certainly well worth the effort. Just to let you know that if you signed up for the single school, June 24th to 28th, make sure that you have blocked off your calendar and that you plan to attend. We're looking forward to that event. So before we begin the talk, I just wanted to say we had our service awards here at Green Bank a couple of weeks ago. And I just wanted to point out that our host of the Green Bank Community Zoom, our erstwhile host, Jay Lockman, has achieved 50 years of service with NRAO and Green Bank. And so I just wanted to applaud Jay for all of his hard work. Jay is the face of the Green Bank Observatory and has been one of its most outstanding scientists. So we are very grateful that Jay has chosen Green Bank as a home, and look forward to another 50 years of Lockman's research. So take it away, Jay.
Thanks very much, Jim. Whoops, I've lost my screen here somehow. Yeah, okay, thank you very much, Jim. Our speaker today is Sanskriti Das from the Kavli Institute in Stanford, speaking about a deep search for missing accretion in the circumgalactic medium. And let me remind everyone that this webinar is being recorded for future viewing and will be available in a day or so on the GBO website. And if you have questions, please use the Q&A button at the bottom of the screen to submit them, and we will get to them at the end of the presentation. Take it away, Dr. Das.
Okay, can you see my screen?
Yes.
Okay, all right. Hello, everyone. So today I'm going to talk about some of our recent findings on diffuse circumgalactic neutral hydrogen, which could be fueling the missing accretion for nearby galaxies. So a bit of context. We expect neutral hydrogen to be the raw fuel of star formation. The neutral hydrogen has to first form molecules and eventually form stars. And if we look at the nearby galaxies, where we can resolve the galaxies well and calculate the depletion timescale, which is basically the ratio of the total mass in neutral hydrogen to star formation rate, it's really small, and it indicates the galaxies might run out of their fuel really soon unless new fresh neutral hydrogen is accreted continuously. And this accreted H1 can also be observed, and the accretion rate can be calculated. If we assume the conversion from neutral hydrogen to stars to be 100% efficient, we would expect the accretion rate of H1 to be exactly same as star formation rate. Or if it's less than 100% efficient process, we would expect the star formation rate to be smaller. But what we find in reality is that the accretion rate is actually an order of magnitude lower. So it might look like the stars are forming out of nowhere, which looks kind of unphysical, and it indicates there might be a lot of hydrogen in the circumgalactic medium outside the disk of galaxies. But since the surface brightness is really low, that makes it really challenging to detect. Now, using Lyman alpha absorption in UV, which can reach really low column density, people find a lot of neutral hydrogen in the CGM, but it is often saturated but undapped. And that indicates a range of column density between 10 to the 16 to 19. And also, it doesn't really give you the radial profile of hydrogen around individual galaxies. It's only an average of many galaxies. So to map the neutral hydrogen around individual galaxies and understand how it correlates with the star formation rate, we need the 21 centimeter emissions. Now, in last 10 years, 10 to 15 years or so, there have been a couple of interferometric surveys which are deeper than the pre-existing surveys like HaloGas, Mongoose, and Wallaby. And all of them have tried to map the CGM at a better sensitivity than before. And some of them have found a bit of extraplanar gas, which is beyond the H1 disk, but it is still not the extended CGM, and it doesn't account for the missing accreted H1. And one of the reasons might be that because of the limited UV space probed by the interferometers, there is always a limit of the maximum angular scale that the interferometers can probe. And the diffuse H1 might have a larger angular scale than that. And to probe all the angular scales together, we require the single dish observations, again in 21 centimeter emission. And for that, GBT is probably one of the best options, if not the best. So it has the unblocked aperture and a pretty well characterized beam with all the side lobes. And also its surface brightness sensitivity is pretty good, which makes it a good candidate to look for low column density, 21 centimeter emission. There have been a few projects using GBT to look for the diffuse H1 before us. One of them is the Amiga, which tried to map the H1 around Andromeda, but really ended up with a non-detection, indicating that too close, too nearby galaxies might not be the best candidate. There has been another survey called GBT HaloGas, where the galaxies are already surveyed with HaloGas were mapped to GBT at a better column density sensitivity than before, around 2 times 10 to the 18 per centimeter square. And they detected H1 out to almost 50 kiloparsec with GBT. But once it was compared with WSRT, it turned out that GBT detecting is contamination by the disk itself convolved with the GBT beam. So there was no trace of extended H1 in the CGM. And from the upper limits, it turned out that the column density of diffuse H1, if it exists, has to be below 10 to the 18 per centimeter square. But going deeper with the whole mapping requires a lot of time, and that is not really feasible for a large number of galaxies. So instead, we take an alternative approach, and we consider a small spatial sampling. But at each point, we stare for a really long time, making the effective time of observation around 3 to 4 hours. And that makes our sensitivity level 2 orders of magnitude deeper than the previous observations. We also focus on age-on galaxies so that we can study the minor axis and major axis and regions in between separately and study the azimuthal variation in detail, which we can't do for low inclination or phase-on galaxies. So we started with 2 nearby very well-studied galaxies, NGC 891 and 4565. There, some of the properties like stellar mass and H1 mass are pretty similar, but star formation activities are absolutely different. So we expected the H1 to be in the CGM to be somewhat different for them. And we observe the CGM in 3 GBT projects with a lot of time, almost 200 hours of observation, including all these 3 projects. Now, getting deeper also makes the analysis harder because just a simple polynomial subtraction doesn't allow us to detect the signal. So instead of just a polynomial subtraction, we had to develop another iterative modified polynomial baseline subtraction routine where we smooth the data at different velocity resolutions. For each of the velocity resolutions, we choose a range of baseline. And we use a modified polynomial, which basically fits the data with a dummy polynomial, then subtract it from the data and reject the others, that is, all the channels that might be 3 sigma away from whatever the scatter is, and it fits the data again. And it gives a better description of a polynomial than the standard one. And we start with assuming there is no emission, which you can see in this leftmost plot. And after the first fit, it finds candidate emission. In the next loop, it removes this candidate emission region from the fit and tries to fit another baseline again. And it repeats until we reach the convergence of the candidate emission. So this is the example of just one pointing, and we repeat this for all the pointings separately. And after doing this, we compare the final results for different velocity resolutions and choose the one where we reach the optimal signal to noise and the column density. In most of the cases, we reached convergence within 5 or 6 loops. Here we reach convergence with just 3 iterations. So we do this for all the pointings, and we were really lucky to detect H1 emission at literally all the pointings out to almost 100 to 120 kiloparsec along the major and minor axes around both of these galaxies. Now, some of these pointings which are 2 to 3 beam size away, they're not significantly affected by the central disk itself, but the pointings which are next to the disk, they are significantly affected. And you can see from this single horn or this broad emission, we the contamination of the disk. So we need to assess the contamination. That's why we use the interferometric data. So we take the data cube from Hello Gas survey. We convolve that with the GBT beam that includes all the side lobes and everything. All of our pointings are within this red dashed square. So we have the information about the GBT beam in this region. And after convolving, we get something like this. And at each of the relevant pointings, we calculate the column density. So we compared the column density from our GBT data, which is shown here with the field points, and compare with the WSRT data, which are shown here with these empty points. So these empty points are basically contamination from the disk plus any high column density emission in the extraplanar region. And as you can see, at all the pointings, the black ones are higher than the empty points. So near the disk itself, which we call 1 GBT detects almost 30 to 40% excess than the WSRT, which is the gas in the CGM. And GBT detects almost 6 to 20% excess, which is even higher. So to summarize this slide, we detect diffuse H1 at all the pointings out to almost 100 kiloparsec. So now that we have the excess, we can subtract the contamination from the GBT column density and calculate the column density from the CGM, and also calculate the mean line of sight velocities to see whether it is in the rest frame in the galaxy or is moving. So here we find that the overall mass is roughly same for both 891 and 4565, but 891 has a much steeper profile, indicating it has more H1 in the immediate vicinity than 4565. And is consistent with the bathtub model, which indicates that galaxies with higher star formation rate should have more H1 in their immediate vicinity. And here on the right-hand side, I show the main line of sight velocities for all the pointings. Here, the field points are again major axis and the empty points are minor axis. So here you can see again that the major axis pointings are co-rotating with the disk, and up to almost 100 kiloparsec, we see that the disk is, the CGM is co-rotating, and that indicates the large-scale accretion. We also find a velocity gradient along the minor axis, which is consistent with an inflow. We find that in both galaxies. And we also discuss in the paper that an inflow and fountain could have similar velocity profiles. So we can't really distinguish between a possible fountain or an inflow, but it extends out to a large distance. And we can calculate a couple of things from this distance, so accretion time and the ratio of accretion rate to star formation rate. For 4565, it turns out that most of the H1, accreting H1 is in the CGM, and it has a sustainable supply to continue the star formation for a really long time. But 891 is not like that. We didn't find most of the accreting H1. And whatever we take, if that is all the H1 it has, it will really run out of H1 relatively soon. And if we calculate total mass in the CGM neutral hydrogen, we find that more than 50% of the baryons are still missing, which means there be more gas in water phase that cannot be traced with 21 centimeter emission. And that's just for the along the principal axis. We are continuing this with other GBT observations. So in the left, I'm showing one of the examples that's being led by one of my students, Mary Riegel. Here, probing the off-axis regions, that's the region between major and minor axis. And here we are trying to do the same thing as before, but we realized that assessing the contamination by the disk needs to be done more carefully than before when we are looking at the off-axis. So this is the result we just got this week. It's a very new result, but when we do more analysis, we'll have a better understanding. But overall, we find that GBT detects roughly 35% excess H1 around 891, but only 20% excess around 4565. Again, we are finding more H1 around 891 than and I'm showing just one example. This is being led by another student, Annie Cheng at Stanford. So here we are looking at galaxies. 891, 565 are both Milky Way mass galaxies, but these are all below 10 to the power 9.5 solar mass in terms of stellar mass, and they have a wide range of star formation rate. So here we observed 4 low mass galaxies with very different star forming activities. And now we are looking at the minor axis pointings of one galaxy here. We detect H1 out to almost 100 kiloparsec at 4 pointings, 5 pointings actually. And in 1 pointings, this is the first time we also have a non-detection. So this is again a very new result. We get this is the termination by disk and so on. In fact, we are still detecting H1 out to a large distance, even around the mass is promising. So in the cycle, we are planning to now observe the major axis pointings and see if they have similar H1 profile, same as the more massive galaxies. So yeah, that's pretty much of what I had. And I'll just summarize by saying that 21 centimeter emission studies using both single dish and interferometer are required to look for the missing diffuse H1 in the CGM of nearby galaxies. And with great data also comes the responsibility of developing new and novel data analysis techniques. We also need to have a very good knowledge of the GBT beam, because that's what we need to convolve with the interferometer cube. And we need to observe a large number of galaxies to understand the diversity of mass distribution and velocity distribution of H1 in the CGM, to understand how it contributes to the star formation, as well as how it contributes to the missing baryons. So having said that, I will stop and take questions and leave you with this link of the paper listening.
Thank you very much. Please submit your questions into the Q&A button on the bottom, and we have several questions already. The question is, the first question, what compels a gas in the halo to accrete?
Oh, that's a nice question. So the basic thing is the gravitational pull of the gas. If this is the cold gas, there is a certain free fall time scale of the gas. So if you think in terms of a cloud, depending on its density and its distance from the galaxy, which gives you a rough estimate of the surrounding density of the gas, one can calculate the free fall time scale. So if there is a cloud in the halo, that will eventually fall onto the disk anyway. And to conserve the angular momentum, it has to accrete roughly in a disk geometry. So that's roughly the reason why the cold gas in the halo accretes onto the disk.
Here's another question that you may have already answered. Using the WSRT image as the ground truth may be misleading, since interferometers miss much of the extended smooth emission, underestimating the amount of gas. Is using the interferometric data to estimate the total emission strength likely leading to a misleading estimates of what you would expect the GBT to detect?
Not really. I mean, the reason we are using interferometers is because it miss most of the extended emission because of the limited UV spacing. So what we detect from WSRT is the small scale emissions. And in GBT, we detect all the scales. So when we find an excess in the GBT, that will be the extended emission. That is the underlying principle.
And would you remind us again of the difference in column density sensitivity between the Westerbork spectra and the GBT spectra?
Yes, so the GBT spectra, 1 sigma sensitivity is 10 to the power 16 per centimeter square. But in the WSRT, it's, I think, 2 times 10 to the 18 per centimeter square.
Thank you. Some more questions. Up to what redshift do you have sufficient sensitivity to detect extended CGM gas?
So for now, we are just focusing on very nearby galaxies within 20 megaparsec. Because one, we need to first be covered by the interferometers, and secondly, if we are too far, the beam of GBT is almost 9.1 arc minute, right? So if it is too far, it will basically, sample a very large region of the galaxy. And if there are filaments or something which has a less than 100% covering fraction, we might actually undersample the gas and might not detect the true distribution. So for now, redshift is not our focus at all, but eventually we might extend it to larger distances. Right now, it's just nearby galaxies.
Here's another question. Can magnetic fields affect the free fall time?
Short answer is yes, and especially in fountains, or basically, in outflows or fountains, if there are magnetic field lines, they kind of align the motion of the clouds. So it will be like a tube that is, so the magnetic fields kind of form a tube kind of thing, and the clouds can follow the magnetic field lines to fall. Depending on the geometry of the magnetic fields, it might have a positive or negative effect on the free fall time scale, but it's hard to say whether it will be just one in case of a single galaxy.
Another question. Could the diffuse H1 be non-homogeneously distributed and perhaps found concentrated in filaments?
Yes, absolutely. We do not know about the exact geometry of the diffuse H1. I didn't discuss it in this talk, but depending on the accretion mode, the morphology can be significantly different. In lower mass galaxies, which we are observing now, they are more likely to be in filaments than just like a fuzzy blob of gas. And in more massive galaxies that we have observed so far, it is supposed to be more like a fuzzy blob. So the theoretical prediction is that the morphology will depend on the low mass or high mass end. But we are, we need more data to verify whether it is a filament or a diffuse gas, depending on what galaxy we are observing.
Here's a question. Are there observations of ionized gas in the CGM of these galaxies? Say X-ray or UV observations? The missing diffuse H1 might be ionized.
Yes. So for these two galaxies, I am not aware of any extra UV observations, but in slightly further away galaxies, there are lots of observations. I mean, in UV, I already mentioned that Lyman alpha observations exist. And there are many like observations of ionized metal like silicon 2 and 3, carbon 2 and 4, and so on. So there is a lot of cool CGM around similar mass galaxies, but these galaxies might have a lot of hot gas in X-ray. And there are 1 or 2 galaxies where X-ray has been detected in the CGM, not in exactly these galaxies, but of similar mass.
Okay. There's a question. Is it possible to identify gas coming in which might create a counter-rotating disk?
Oh, yeah. I mean, it is not impossible. We are just finding the H1 to co-rotate in these two galaxies. But in other galaxies, it is not impossible to counter-rotate. But in that case, it would kind of be affecting the accretion process in a negative way. So I hope there is not much H1 like that, but if there is, it's not impossible.
Mhm.
So, yeah.
Let's see, here's a question that just came in. Could the dark matter be dispersing H1 in regions beyond the edge of this galactic star formation, I think? I'm not quite sure. I'm not quite sure I understand that question. Yeah.
Yeah, I didn't understand it completely either.
Here's another one. What is the evidence for accretion of this gas in the galaxy? And do you see a bar in the galactic disk?
As far as I know, these galaxies do not have a bar, and the evidence of accretion in the CGM is coming from the velocity profile.
Okay. Do you, I have a question here. Would you remind us of the difference in star formation rate between the two galaxies and also in the sort of total mass that you're finding in the CGM of H1?
So total mass of H1 is roughly around 4 times 10 to the 8. And the star formation rate of 891 is, I think, 2.5 solar mass per year. And 4565 is 0.6 solar mass per year.
Okay, so it might be that the elevated star formation rate, which you say is not sustainable, that would drop back to a more normal level as it runs out of gas.
Yes, that's possible.
Yeah. Okay.
Or there might be more gas, in the regions that we have not probed yet. We have only probed the major and minor axes.
Well, that finishes our open questions. And let me thank you once again for a most interesting talk. As I mentioned earlier, this talk has been recorded and will be available through the Green Bank Observatory website in a day or two. We are coming into a period of vacation. And so for the next 4 weeks, there will not be any talks. Our website had erroneously listed a talk for June 19th, but that's the Juneteenth holiday. And that talk has been rescheduled for later in the summer. And the next talk after that would be on July 4th. So please join us again in 4 weeks, 6 weeks, 6 weeks on July 17th for Spandan Chowdhury speaking on infall in the subsonic filaments of B5 core using ammonia observations. Thanks very much, and we look forward to seeing you then.